Page 14. Page 5. Okay, so h is sine 2x equals cosine x. Okay, now there's actually one identity, or there's a couple identities that's going to show up here. This one is double angle identity, sine 2x. So sine 2x is two sine x cosine x. The 2 cosine squared x minus 1, that's cosine 2x. So cosine 2x has 3 variations, but there's only one variation or one thing for sine 2x. Okay, so there's my get that 2x out of that double angle identity, and then it becomes sine x cosine x. A little bit easier to work with when we're down to x. So I can replace this piece with 2 sine x. All right, so now I have everything. And though I don't have everything being one trig function, but we can go through maybe some factoring steps here. Let's bring everything over to one side. Now we can factor, right? So factor between these two terms, I can take out the cosine x. That's right. So we asked where is cosine equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2. Sine of x, solve for sine x, I get 1/2. So sine is positive in the first and second quadrant. It's going to be in that pi over 6. Yes, right, pi over 6, pi over 6. That family there. Okay, so we have 4 solutions. Hey, morning. All right, part H look good. Yeah. Okay, so now part I, same idea, but we actually don't have to worry about an identity here because if we approach it the same way, we can bring everything over to one side, set equal to 0, and then GCF again. So GCF between these two terms is cotangent x. Factor cotangent x, I'm left with cosine x, cosine squared x minus 2. And I set both equal to 0. Now, it may not be apparent as to where is cotangent equal to 0, but I like to think in terms of sine and cosine. So if I can get cosine over sine as cotangent, then really it's just the numerator. So if we're ever setting a fraction equal to 0, with both numerator and denominator having a variable, if they don't combine, then you can just set the numerator equal to 0. So if I set the denominator equal to 0, that's something else. That's a vertical asymptote. If I just set the numerator equal to 0, it's basically asking where is this graph going to cross the x-axis? So that's basically just that numerator. So it becomes a lot easier. Where is cosine equal to 0? Pi over 2, 3 pi over 2. And then the issue here, if I try to solve for cosine x, I get plus or minus square root of 2. And the issue is that square root of 2 is around like 1.2. And if you look at your cosine function, your cosine graph will look like this. Right. It's always going to kind of go back and forth between -1 and 1, so it's a little bit too high for this graph to reach, so it's undefined.
Maybe see page 13.
Okay, so we want to do sine of arctangent 3x. Okay, so we always want to focus our attention in this portion first, right? This feels messy. So the idea is if I can create a triangle for this scenario, then I can just read off of that triangle and find sine of that triangle. But first, arctangent 3x, that's another way of saying it is, what would it look like if tangent of theta is equal to 3x? Okay. That's just rearranging it, getting that. Right now, this is theta. And then if I just kind of go back from arc trig to trig function, I get tangent theta. So tangent theta equals 3x. Now 3x, I like to put a denominator there because we think in terms of ratio here. So ratio for tangent is SOHCAHTOA is opposite over adjacent. Right, so we're going to create a triangle with this characteristic. Right, so I'm going to draw a triangle here, first quadrant. So tangent is opposite over adjacent. So 3x is my opposite. Adjacent is my 1. I'm going to use this information to fill out my third side. Pythagorean theorem says a squared plus b squared equals c squared. So a squared plus b squared equals c squared. Clean this up. C squared equals 1 plus 9x squared. Take the square root. Solve for c. Square root of 1 plus 9x squared. So that goes here. So I'm to get all this in just by looking at that arctangent 3x. So now that I have that in, sine of theta is just opposite over hypotenuse, SOHCAHTOA. And you don't have to rationalize the denominator. You can leave your radical in the denominator. Okay, does that make sense? Okay. Mm-hmm.
For A, basically, your answer in general form is that A is supposed to be the C for 0.
It says general form, but you can do any form. So I think I just did like point slope form or slope intercept form. Yeah, number 8. Yeah, I did it in point slope form. There's no need for general form, but yeah, general form would be ax plus by equals c. Mm-hmm. So which one? Just B. Okay. Right. So first thing you want to do is you want to solve for y. So get y by itself. Y equals -5/2 x plus 7/2. And really, the only thing that we care from this equation is just the slope, right? We want to create something that has a parallel slope. So my slope from this line is -5/2. So that's the only thing I care about from this line. I'm going to use the point that they give me. And so if I have my slope and if I have my point, then do point slope form. And then for part B, normal means perpendicular. So I'm going to take the same slope that I gathered from part A from the equation. I'm going to create a perpendicular slope from -5/2. So perpendicular slope means I'm going to swap the numerator and denominator values and change the sign. So -5/2 flip becomes 2/5. So now I have my new slope. I'm still using the same point that they gave me, and then point slope form.
Got it.
Mm-hmm.
Six.
Mm-hmm. Yeah, it looks messy here, but you're going to use the 2 points they give you to find the slope. So change in y over change in x. Clean it up, you get your new slope. And then you can either use the first or second point to create your equation. So this is what using the first point would look like. This is what the second point will look like. These look different, but if you were to get y by itself, both equations, they're going to look exactly the same. So this is point slope form, but they both refer to the same equation. Just looks a little bit different because 2 different points.
Or C.
Mm-hmm.
32.
Yeah, this one requires also the use or the need of double angle. This is page 13, part C. The hope is that trying to get that cosine to be in terms of sine. So if everything is in terms of sine, then I'll have an easier time. Also, double angle makes it difficult to work together. So there are 3 variations of double angle identity for cosine, and I want to choose the one that involves just the sine. So the hope is that if I get everything to sine, easier to work with. So cosine of 2x is equal to 1 minus 2 sine squared x. So there's my substitution. So once I make that substitution, I still have that minus 1 left over, but have everything now in terms of sign. So what if we bring everything over to one side and see what we can do with factoring? So looks like the 1 minus 1 cancels out. All right, GCF, sine x. So I'm left with 2 sine x plus 1. All right, we ask ourselves, where is sine equal to 0? Now, normally I would include 2 pi. Yeah, because of that inequality there. That less than doesn't include 2 pi, so we can actually remove 2 pi. Where's sine equal to negative 1/2? That's going to be in that pi over 6 family. Sine is negative in the 3rd and 4th quadrant. So again, 4 solutions. Good. Anything else? You guys keep looking. Yeah, there's no rush.
You did 4.
This is page 13. Page okay, page 13. So yeah, it doesn't look like they share the same equations, but there's no need to convert everything to be one trig function. If I just bring everything over to one side, I can clearly separate the sine and tangent by just factoring out the sine. So once that sine gets factored out, it becomes easier. So looking for sine equal to 0 and looking for tangent equal to 1. Tangent is equal to 1. That's in the first and third quadrant in that power 4 family. So power 4, 5 power.
We do page 1148.
Hey, e to the 2x equals 1. I want to solve for x, but x is stuck in that that exponent location. So we have natural log properties to help us with that. So I can take the natural log of both sides. Exponent is free to come down, so that exponent comes down. 2x natural log of e equals natural log of 0. So we have some special properties here. Sorry, natural log of 1. So special property is that natural log of 1 is equal to 0. And then and natural log of e is equal to 1. So that becomes 1 and 0. Becomes easy now. 2x equals 0. Solve for x, divide both sides by 2. X equals 0. And then another way to quickly get through this is, it's not going to work every time, but if you look at this and said, okay, e raised to what power is equal to 1, basically if I force that x to be 0, then anything raised to the 0 power is 1. So that's why x is equal to 0.
Morning.
Thank you.
Mm-hmm.
And when do we do the calculators again?
I would say probably sometime after Labor Day. Oh, no, you have a little bit of time.
Thank you.
Mm-hmm.
See you.
For ones, these problems, but
Uh-huh.
I don't remember how to do them.
Uh-huh.
Like,
Right. So, right. So first things,
Here, I'll put it up on the board in case Charlie can see it as well. So this is, what page is that?
14.
Okay, so sine 4x equals 1/2. You got the first steps right. Get that x, that 4x by itself. And that when that sine comes over, it becomes inverse sine. So in other words, this is basically asking where is sine equal to 1/2, right? So we're going to just solve the one problem at a time. Not going to worry about that 4x just yet. Where is sine equal to 1/2? Well, sine is equal to 1/2 in first and second quadrant, right? So in that pi over 6 family, so pi over 6 and 5 pi over 6. Right, you go with that. Okay. Now, we could just divide by 4 and solve for x, which is fine. But the problem is that when this is only in the first and third quadrant, when it shrinks by this much, it's going to be even smaller. And we're not going to be able to get all the solutions because everything is shrinking. So we need to go past the first, go past the first and second, third iteration so that when everything shrinks, all the solutions are still lined up between 0 and 2 pi. So we have to go further out than what we would like. And to go further out, we're going to add 2 pi. Because if I add 2 pi, I get more locations where the sine is going to end up being 1/2, because sine is going to keep oscillating and it's going to eventually hit these 1/2 over and over again. So to find more coterminal angles, we're going to add 2 pi. So add 2 pi is same thing as plus 12 pi over 6 if I want to match the denominator. So I'm going to keep adding these two here. So 1 plus 12, this is 1 pi over 6. 1 plus 12 is 13. So 13 pi over 6. Add the second initial. 5 plus 12 is 17. So 17 pi over 6. And then whatever I add, I'm going to keep adding more. So 13 plus 12 is 25. 12 plus 17 is 29. And we have to go out even further here. So I'm going to keep adding here. And then, sorry, I didn't put the instruction for this one because that 4x requires a ton if I want to get 2 pi. So I just said solve for x between 0 and pi. So I think I can stop here because what happens is if I divide both sides by 4, that's the same thing as multiplying by. So then x equals, the 4's cancel out. So multiply all my denominators by 4, I get pi over 24. 5 pi over 24. So I'm looking for anything up to pi, and pi is where my numerator and denominator is the same. If uh, but once my numerator becomes larger than my denominator, then that's more than pi. So I know I can remove these two. This is a little bit too far out.
Is I was like, that was the resection that it's showing.
Yeah, I can go over any ones you want me to go over.
See.
Yeah, part C, there's a double angle identity needed here. So if I can get that cosine 2x to be represented by sine, it makes it easier. So there's an identity for cosine 2x, which is 1 minus 2 sine squared x. So the advantage there is if I can get that cosine 2x to be 1 minus 2 sine squared x, now all of a sudden, every one of these terms in terms of sine and then factoring wise, it's a little bit easier to work with. So get everything over to one side, factor that sine out, and then it becomes more straightforward.
Suddenly to 0 and
Right. Set it go to 0 and then look for your unit circle values.
this is a stupid question, like, because they the same name. How like,
Mhm.
what's the first step?
I can take out a GCF.
GCF,
So GCF is e to the x.
Oh, okay.
Yeah. Hey,
Hey, how are you?
Good, how are you?
I just wanted to ask you if you might be able to review my letter.
Sure. Yeah.
I could like send you an email.
yeah. Yeah, that'll be good. I don't know if they're still using Naviance, but I think once I find out, you know, what platform we're gonna be using. But yeah, just send me an email
Okay.
and I can at least put that, to start working on.
For sure. Yeah.
Okay.
Thank you so much.
Yeah, sure. All right, have a good year.
You too.
Yeah.